degrees. As it rises, its vertical component of velocity. Well, we know the rock's thrown upward at 50 degrees. I like to always draw in a picture for my problems. So you have some rock, it's thrown upward at this angle. Say that's 50 degrees with the horizontal. We know the path of this rock. It's going to look something like a parabolic arc, right? As it is rising, as it is moving upwards, what is going to happen to that vertical component of the velocity? Is that velocity in the y direction? Well, you can just think about if you toss a tennis ball upward, is it going to speed up? Is it going to slow down on its way up? Well, it is going to, of course, slow down on its way up. Explaining the answer, well, it has a constant negative acceleration. Negative acceleration. That means that as it's moving upwards, it has a negative acceleration, it's going to slow down. As the rock in problem number 1 rises, horizontal component of velocity. Well, we know horizontally, in that x direction, the acceleration is 0 meters per second squared. So, since there's no acceleration, left or right, that horizontal component of the velocity, that velocity in the x, is going to remain unchanged. It's not accelerating, not changing speed or velocity. Number 3, true or false, speed of a projectile stays the same for its entire flight. Well, let's use our previous answers. We know the vertical component is decreasing as it's moving up. That horizontal component is remaining unchanged, but speed is really just looking at the magnitude of the velocity. Since it is going throughout the whole flight, it's going to be changing. We know the vertical component's changing, so its speed must be changing as well. The speed of a projectile is not the same. A projectile, by definition, the only force acting on it is gravity, so it is going to be accelerating. Accelerate. With the acceleration in the y direction being that negative 9.8 meters per second squared. The speed of a projectile is 0 at the top of its flight. So here, speed of a projectile is 0 at the top of its flight. Well, let's look at this previous problem. Rock is thrown upwards. As it rises, its vertical component of the velocity, we know at the very top, that velocity in the y direction is 0. But it is still moving to the right. So here, some projectiles, if you launch something straight up at the very top, it is not moving up, not moving down, not moving left or right, then its speed would be 0. But you can imagine if you launch something at an angle at the top, vertically, its speed is 0. But horizontally, it would still be moving. So speed of a projectile is 0 at the top of its flight. That is false. A projectile can be moving left or right at the peak. Okay, let's move on. Number 5, 2 dogs fire a cannonball from the ground. They're trying to determine if complementary launch angles that add to 90 degrees, create any interesting results. Maple fires her cannonball at 25 meters per second at an angle of 20 degrees above the horizontal. Calculate the distance the cannonball travels while in the air, the maximum height reached, and the amount of time in the air. Okay, so in order to do this, we are definitely going to need some space. Let's draw our picture. I always love having a picture. We know we are launching. We're just on some flat surface. We are launching a cannonball from the ground. Since it is being launched at an angle, will follow this parabolic trajectory. Let's draw our arrow to represent that launch. So this is our velocity. Maple's firing the cannon 25 meters per second. Let's fill that in. We go ahead, break this up into our components, we have our vertical and horizontal components. This is our initial velocity in the x direction, our initial velocity in the y direction as well. Our angle here, we know, is 20 degrees. We want to calculate that delta x. So right here, delta x is something we're solving for. We want to calculate that maximum delta y and the total time we spend in the air. Well, we always want to start off with our xy chart. So let's just draw that right in here. Let's start with our hidden givens. We know for a projectile, we're in the air, the only force acting is the force of gravity. So, since net forces, total forces, cause acceleration, the only force is downward, the total force is downward, that acceleration must also be downward. So there is no acceleration left or right. By contrast, vertically, in the y direction, we have that negative 9.8 meters per second squared of acceleration. Let's find our initial components of our velocity in our x and y direction. We can do that just looking at our launch angle right here. We have equations for both of these. We say that the initial velocity in the x is just our velocity times the cosine of our angle theta. Initial velocity in the y is our velocity times the sine of our angle theta. If we plug those in, well, our velocity is 25 meters per second times the cosine of our angle, 20. For our y direction, that is still just 25 times now our sine of that angle, 20 degrees. Make sure you're using your degree mode on your calculator here. So we'll actually just exit out really quick, bring up our calculator, and make sure we're using degree mode. So we have the sine of 25 gives us some decimal. Multiply that by our velocity, I believe it was 20. 8.45. Let's go back into Notability. Make sure we did that correctly. Okay, I did swap our angle and our velocity. So let's redo that. Our angle is 20, our velocity is 25. So we'll say sine of 20, that angle. Plugging in the angle's 20. Then we're multiplying by that launch velocity, which is 25. Get our answer here, 8.55. That was our sine, so that is our initial velocity in the y direction, 8.55 meters per second. Let's do that now for our x direction, so we'll be using cosine. So you'll say the cosine of our angle, 20, cosine 20. Multiply that by our 25, we get 23.49. All right, 23.49, perfect. Let's add that into our chart. It's right here. Initial velocity in the x, 23.49 meters per second. Initial velocity in the y is 8.55. Okay. We have our two variables. Now here, with our angle launch problems, this is where you have to think about what else you know, what else can you pull from the problem. Let's start off and say, let's identify a critical point during this problem. If we go back up to our diagram, let's look at the top. Right up here, the very peak of the motion, because we know something really important about the peak of the motion. At the peak, we know that vertical velocity is 0. It's not moving up. It hasn't yet started falling down, so that y velocity is 0. We're going to plug that in as our final velocity in our y direction is 0 meters per second. And this specifically is at the peak of our motion. I'm just adding in that extra subscript saying it's at the peak just so that we're clear this is at the peak of the motion, not at the end of the motion. Now we have three variables. We can solve for the time it takes to reach the peak. We can also solve for that delta y, and really we have options. We can go through and we can solve it in whatever order we want. Let's write out our equations using our x variables. So for the horizontal direction, that horizontal displacement is equal to the initial horizontal velocity multiplied by the time plus our 1/2, the acceleration in the x, times our time squared. We also have that the final velocity in the x is equal to our initial velocity in the x plus acceleration in the x multiplied by our time. And our last equation is our final velocity in the x squared is equal to our initial velocity in the x squared plus 2, the acceleration in the x direction, multiplied by that displacement in the x direction. So those are our equations. Let's pick which one to use. Here it doesn't really matter what we're solving for first. You have three variables, the acceleration, initial velocity, and final velocity at the peak. You can use those three variables to either solve for your time at the peak or your maximum delta y. Let's go through and let's solve for our time to start. To do that, we are going to use our equation right here. So if we use that equation, we just start plugging everything in. The final velocity for our y direction is 0, or at the peak. Let's tack our units on there, just to show that everything cancels out. Our initial velocity, 8.55 meters per second, plus the acceleration in the y direction, negative 9.8 meters per second squared. Our time is what we're solving for. Now we just want to isolate our time. We'll move the 8.55 over, subtract it from both sides. That's going to cancel out on our right-hand side and give us on our left-hand side negative 8.55 is equal to negative 9.8 meters per second squared times our time. Now, and we want to remember our units over here. Now we're going to divide both sides by our 9.8. If we do this, we can solve for our time. And this is the time to the peak. So let's use our calculator. I'll use my calculator off to the side here. We're just plugging in 8.55 dividing by 9.8. And we get the time to the peak, 0.87 seconds. Let's round to that second decimal. Now that's the time to the peak. If we want to get the time total, well, since we know we're on an even surface, right up here, on an even surface, we know, right up here, even surface, the time it takes to get to the peak is going to be the time it takes to fall back down from the peak. So, if it takes 0.87 seconds to reach the peak, the total time then is just twice that 0.87 seconds. So we'll take our 0.87, multiply it by 2. The total time is 1.74 seconds. Let's plug that in for our answer right here. So you can go ahead, highlight that. We used our pink equation to get that answer. Again, that was the time at the peak. We doubled it to get our total time. Now let's take a look at something else. Let's look at that delta y. Here, we have our time, we have our final velocity at the peak, we have our initial velocity, and we have our acceleration, all in the y direction. So we can use either of our other equations to solve. All right, let's look at that max delta y. So here, let's consult our diagram. We know the time that has passed for it to reach its end over here is 1.74 seconds. The time that will have passed for it to be at its peak is that time to the peak that we calculated earlier, which is 0.87 seconds. Now we want to be very careful here. We want to plug in the time it takes to get to the peak, not the total time, because we want to use the time that has passed when we are at this maximum delta y. So let's use our highlighted equation and just plug everything we have in. So this is our delta y. I'll be saving room, not showing our units here, but rest assured they will all turn into meters. We know delta y measured in meters. They're gonna cancel each other out, turn into meters. So our velocity in the y direction initially is 8.55. Our time, again, we're using the time at the peak, 0.87. Now, we have our 1/2, that acceleration, negative 9.8, and our time, 0.87 squared. All right, now, as for the order I like to plot these things in, I like to combine our 8.55 and 0.87. Let's just multiply them. 8.55 times 0.87. We get 7.44. Let's round to that nearest hundredth place. Plus, I like to start with my squared term so I don't mess anything up. 0.87 times 0.87. Multiply them together. For that term, we get 0.76. That is 0.87 squared. Let's combine our negative 9.8 and 1/2, multiply them together. We'll get negative 4.9 here. Now, we just need to take our 4.9, take our 0.76, multiply them together, and we will get our answer, 3.72. Can't forget, we have our negative, so that negative needs to come down. And we still have our 7.44 as well. So really, this is 7.44 minus 3.72. That is going to equal our delta y right up here. Let's do that math. 7.44 subtract 3.72. And we get 3.72. Of course, we know our units there are meters. So that maximum height, 3.72 meters. Okay. Now we just have our last thing to solve for, that delta x. Let's go ahead and solve for that. Using our xy chart right here, we split up our variables into our x variables, into our y variables. We only have two pieces of information right here. We need a third. Luckily, we solved for our time, the total time here. We want to use our total time rather than the time at the peak. Let's plug in that total time, 1.74. We know time, that's what unites our horizontal and vertical motions. So let's use that. And now we are really going to use this same equation that I've highlighted in green, and we'll plug in everything we know into it. Now something really nice is going to happen here. If we write out our equation, we'll see we have this whole second term. Since we have an acceleration of 0 right here, when we plug in 0 to the second term, this is just going to turn into 0. The whole thing is being multiplied by 0, so it all turns into 0. It all drops out of our equation. That simplifies things a great deal for us. Now we just have delta x is equal to our initial velocity times time. Let's plug in what we have. Delta x is equal to 23.49. Our time is 1.74. Let's multiply 23.49 times 1.74 equals 40.87 meters. So you can write this right here, 40.87 meters. Okay. All right. Let's look at part B. Daisy fires her cannonball at 25 meters per second at an angle of 70 above the horizontal. Calculate the distance the cannonball travels while in the air, the maximum height reached, and the amount of time in the air. To do this, we're just going to use our same process, right? We have our picture. It's really going to be a very similar picture, just at a steeper angle. The big thing we have to look at is we now have to change our angle, which is going to change our numbers. We can still make our XY chart, separate out our variables. We still know acceleration in the X, 0 meters per second squared. Acceleration in the Y, negative 9.8. And let's just start off, do all our same steps again. We want to determine the components of that velocity. We still know the velocity is 25 meters per second. This time, our angle is, instead of 20, it's now 70 degrees. Much, much steeper. Calculating our initial velocity in the X, we know that's just the velocity times our cosine of our angle. Velocity in the Y is our velocity times the sine of our angle. I'm running out of space here. If we take our calculator, again, let's plug this in. So let's look at X first. We're going to do cosine 70 times 25. Go into our calculator. We'll take the cosine of our angle, 70, multiply that by 25. Cosine 70 multiplied by 25, 8.55. Okay, this sounds familiar. Initial velocity in the X, 8.55 meters per second. Initial velocity in the Y is going to be that 25 times the sine of our angle 70. So let's go through. Sine of 70, multiply it by our 25, velocity 23.49. Something I want to point out to you, if we look at our previous problem, all that has changed is we've now swapped the initial velocity in the X for the initial velocity in the Y. We've swapped the initial velocity in the Y for the initial velocity in the X. When we use those complementary angles, that's exactly what we're going to find happens. All right, we still want to calculate all of our same things. So let's start the same order we did before. Let's start with our time. We're going to use this same equation right up here. Let's go ahead, try to do a little copying. All right. All right, so here we will say the final velocity. And again, we are going to use our X variables. So final velocity in the Y, since we're using horizontal, I misspoke, we're using vertical. Final velocity in the Y is equal to our initial velocity in the Y plus the acceleration in the Y times time. We can still use this same diagram. It's still going to follow this parabolic trajectory. We just know the time, the total time is no longer 1.7. Let's erase all of that. The time at the peak is no longer 0.87, but what is still true is that velocity at the top is 0. So what we do here is we can write final velocity in the Y. Again, this is at the peak, is 0 meters per second. All right, let's save some room. I'll just write our numbers instead of our units at the end. Final velocity, 0, equals to our initial velocity, 23.49, plus we have our acceleration, 9.8, multiplied by our time, which we are trying to solve for. Same process, we're going to bring this 23 over, subtract it from both sides. It's going to cancel. We get negative 23.49 equals our negative. Need to remember our negative. Don't want to forget it like me. And now we just have to divide. Divide both sides by 9.8. Negative 9.8, that is. This cancels. And we plug into our calculator. Since our negatives drop off, 23.49 divided by 9.8. Our time, 2.396. I'm going to round that to 2.4 seconds. And now we know that is the time it takes to reach the peak of our motion, not the total time. To get the total time, we have to double it. So that total time then, 2.4 times 2, 4.8 seconds. All right. We got our total time. Let's go ahead and add that to our diagram. The total time, 4.8 seconds. The time it takes to get to the peak, 2.4 seconds. Okay. We can double check. I always recommend it's good to just kind of pass the problems through the sniff test. Do the numbers you're getting make logical sense in real life? Does it make sense? Without even any physics knowledge, you would have been able to tell me if you throw something at a steeper angle, so more upwards, versus throwing it more horizontally, it's going to take more time to reach the peak. When we launched it at 20 degrees above the horizontal, it only spent 1.74 seconds in the air. Now we've launched it at a much steeper angle. It's spending much longer in the air. That makes sense. All right, let's keep going. Let's solve for our maximum delta y. We know, and we want to use that equation we highlighted in green, and be very careful. We want to use the time at the peak. So let's say our delta y is equal to our initial velocity in the y times our time plus 1/2 acceleration in the y time squared. Okay. Delta y is what we're solving for. The initial velocity, it's 23.49. The time, this is the time to the peak. So we'll use our 2.4 plus 1/2 that negative 9.8, 2.4 squared. And now we're just going to go through solve just like we did last time. 23.49 times 2.4, 56.38 plus, let's do our squared first, 2.4 squared gives us 5.76. 1/2 times negative 9.8 gives us negative 4.9. We're multiplying negative 4.9 by 5.76. We get 28.224. And now we have to remember, we're subtracting here. This negative comes along for the ride. So instead of adding, we're subtracting. 56.38. Now we just have to plug and chug, like we've been doing. We get our answer, 28.156. Of course, our units there are meters, since we're measuring a displacement. That's our maximum delta y, 28.156 meters. Again, does this make sense? Well, we launched it at a much steeper angle, so that means it was going way faster vertically. It is going to go way higher than it did before. Okay. Now, our last part, let's solve for that delta x. We're going to use that time, that total time, plug it in on our x side, 4.8. And we'll use this along with our same equation, just for our x variables. Delta x equals our initial velocity in the x times time plus 1/2 the acceleration in the x times squared. Just like before, the acceleration is 0, it drops off to 0, that whole term. Now we just have to plug in our 8.55, multiply that with the time, 4.8. Let's multiply. 8.55 times 4.8. We get our delta x 41.04 meters. All right. So here, something interesting we noticed is that when you're launching at complementary angles, those components of our velocities, velocity in the x, velocity in the y, they just flip-flop when you launch at a complementary angle. So angles that add to 90 degrees. 20 and 70, they add to 90, they're complementary angles. Something else we should notice is right here, when we launched it at 20, it went 40.87 meters. When we launched it at 70 degrees, it went 41.04 meters. These are so close. They're really, if we never rounded our numbers, these would be exactly the same distance. If you launch something at complementary angles, they would reach the same distance. 20 degrees, 70 degrees, if you launch it at the same speed, it's going to travel the same distance. All right, part C, which cannonball travels further? Circle the correct response. Again, here, if you're doing this math and you round, you might say, oh, well, Daisy's goes slightly farther. And that's true in the math we did, but that involved a lot of rounding. If we didn't round, they would really travel the same distance. Which cannonball goes higher in the air? Well, that is, of course, going to be the one that's launched at a higher angle. That's going to be Daisy's. Which cannonball spends more time in the air? Well, that's also going to be Daisy's. It's launched at that steeper angle. It spends more time in the air. It goes higher in the air. These are questions that you don't really need your physics to prove. This is something you would be able to just know. Sometimes we can get caught up in all the math and all the physics and just forget our basic common sense problem solving. But just take a step back if you're stressed out on the test trying to solve something that's just a concept. Think about what you know in real life. Take a step back from the math. What do you know to be true? What's going to happen? Well, Daisy is angling her cannonball much, much more vertically, so it's going to go higher. It's also going to spend more time in the air. All right. Let's take a look at number 6. Okay. For number 6, Pope fires 2 cannonballs from the ground at equal speeds but at different angles. One is fired at an angle of 30 degrees and the other at 60 degrees. The cannonball that hits the ground first will be the one fired at, well, let's draw a quick picture. We have one launched at 30 degrees. Let's just do our best guess. Say 30 degrees is something like that. It launches through the air, flies, follows a path like this. Now let's draw out our best picture for 60 degrees. Steeper than 45, maybe something like this. So, we know the one with the steeper angle is going to have a greater initial velocity in the vertical direction. We could break this down into our components for our velocities. Whatever has that bigger angle, it's going to have, again, the bigger initial velocity vertically. So that means that the cannonball that hits the ground first will be the one fired at the lower angle. Like we just saw with Daisy and Maple, the one that is launched at that greater angle, the one that's more vertical, is going to spend more time in the air. It's going to have a higher maximum delta Y value. So here, the one that hits the ground first is the one fired at the lower angle. In problem number 6, the cannonball that travels the most distance is the one launched at. Here, like we saw with Daisy and Maple, these two angles, they are complementary. 30 plus 60, if you add those angles up, they add to 90. That means that a projectile launched at either of those angles will both hit at the same place. The one launched at 60, it spends more time in the air, but it's not going as fast horizontally. The one launched at 30 degrees, it doesn't spend as much time in the air, but to compensate, it's going faster horizontally. So in the end, they travel the same distance. For explaining the answer, it's essentially what I just said, so I don't think I need to write that down. Projectiles launched from the ground rank the magnitude from greatest to least of its acceleration at the various heights listed below. Use equal signs for any values that are equal. Okay, again, we're looking at magnitude here, so that's the strength of something. We're going from greatest to least of its acceleration at the various heights listed below. Any values that are equal. So, we're looking at the acceleration. We know acceleration in the x for a projectile. No forces in the x direction, acceleration must be 0. Acceleration in the y, the only force is gravity. Acceleration due to gravity is that negative 9.8 meters per second squared. Doesn't matter where it's at along its path. Just after it's launched, just before it lands, halfway up, halfway down, at the top of its path, at all points, these are going to have the same acceleration. So our acceleration at A is equal to our acceleration at B, equal to C, equal to D, equal to E. You might remember from our notes, we drew in the path of a projectile launched at some angle, and we said that at each point here, no matter where it is, since the only force acting is gravity, it has that acceleration downward. Same acceleration at each point, negative 9.8. Number 9, while flying in an airplane at a constant speed, you toss an M&M chocolate candy, yelling directly upward. The M&M will land. So here, we're flying in an airplane at a constant speed, toss an M&M candy upward. It is going to land right back in your hand. The reason being, well, you, as a person on the plane, you are traveling to the right with some velocity. The M&M candy, let's say it is a blue M&M. It is also traveling to the right with that same velocity. So when you throw it directly upwards, it maintains that horizontal motion just like you do, and it is going to land right back in your hand. You can think about this, again, going back to real life examples. If you're on a train, and your train is going to some city, you're moving at a constant velocity, you toss a tennis ball in your hand straight up, it's going to come right back down into your hand. If you're in an airplane, wish to give an M&M chocolate candy to the person behind you by tossing it directly upwards, well, the only way you could do this is if you throw the M&M chocolate candy, TM, during takeoff. The reason for this is because when you, right here, let's say this is you have your M&M chocolate candy. Your friend is behind you. Right now, let's say the plane isn't moving. That's good. That means the M&M in your hand also isn't moving. If you throw it up, we'll toss our M&M upwards. Well, then it'll be in the air, not have any velocity left or right. It's a projectile. It's in the air. It's not going to accelerate to the left or right at all either. So it is going to just stay in its place horizontally, not moving left or right. But the airplane, that starts moving to the right. It's accelerating to the right. It's taking off. So the M&M is in the air. Only force is gravity. It's not accelerating or moving left or right. But the airplane starts accelerating. It starts moving to the right. Well, now, let's draw that M&M coming back down. It's not that the M&M has actually moved. It's just that you and your friend, being in the airplane on your seats, have moved. So the M&M lands back in your hand. Okay. 11. A ball is thrown into the air at some angle between 10 degrees and 80 degrees. At the top of the ball's path, its velocity is... So here, and let's draw a picture. It's launched at some angle. We can fill this in. We say its path is going to follow our parabolic trajectory, at the very top, well, we know the velocity in the y direction is 0. It's not moving up, it's not moving down. The trick here is it's still moving to the right. So it has no vertical component. We know those answers are wrong. Its component of velocity is entirely horizontal. That is true. But a more specific answer is the component of our velocity is dependent on the initial angle. But we really want to go with entirely horizontal here. It is true the velocity at the top of its path is dependent on the initial angle, but it is also entirely horizontal. Number 12. An airplane is flying horizontally over an airfield at a speed of 40 meters per second. The pilot drops a sack of mail, which falls for 4 seconds. Ignoring air drag, when the sack hits the ground, it is... Excuse me. All right. So here, let's draw a picture, like we always like to. We have a plane. Let's say that's a plane. It is flying horizontally over some airfield. Right here. It is flying at a speed purely horizontally, velocity in the x direction, 40 meters per second. They drop a sack of mail, it falls for 4 seconds. Ignoring air drag, the path this mail is really going to take, a lot of people would like to say, oh, it's just going to fall straight down, right? Well, what we're really going to see is because that sack is released at the speed of the plane, it is really moving to the right at 40 meters per second and will follow a path something like this. This is essentially just a fancy way to say this is a horizontal launch problem. When you drop the sack of mail rather, just like the skydiver, they jump out of the plane. Initially, that initial velocity in our y direction is 0, but your initial velocity in the x direction is 40. So just like a horizontal launch problem, a tennis ball rolling off a table, just like the car crash lab or the falling ball lab, horizontal launch. So here, when the sack hits the ground, it is going to be directly beneath the plane. The reason for that being, the sack of mail is moving 40 meters per second with the plane. The plane is moving 40 meters per second. Once it is dropped, it is still at the speed that the plane dropped it, at that 40 meters per second. This component is not going to change. Our acceleration in the x is 0. So, since it is moving at the same speed the plane is, it will fall and land right beneath the plane. All right, we're in the home stretch here. To determine the speed of a horizontally thrown ball, Phil Physics, what a good name, measures the horizontal displacement of the ball from his location to where the ball hits the ground. What other single piece of information could he use to calculate his pitching speed with one equation? All right, so Phil Physics wants to determine the speed of a horizontally thrown ball. So that would be the initial velocity in the x. That is what he's trying to determine. They measure the horizontal displacement. Horizontal displacement, delta x, is some value. What other single piece of information could he use to calculate his pitching speed with one equation? Well, this is very similar to our falling ball lab. We had our ball. What we were able to do is we were able to determine that initial velocity with two things. You had to measure your delta x, and you had to measure your delta y. So what we are missing is our delta y. If we were to have our delta y, we would then be able to say, well, we have our delta y, some value. We know our acceleration in the y direction is our negative 9.8. And we know that that initial velocity in the y is 0, since we are launching it horizontally. With that delta y, now we can find the pitching speed with just one equation. All right. Now, number 14, you throw a ball 20 degrees below the horizontal while dropping a rock at the same time from the same initial height. Which object will hit the ground first? Here, it is going to be, so we're throwing the ball. So in green, we have the ball. In blue, we have the rock. Let's separate those out just so we know which is which. Here, let's look at the initial velocity of each. For the rock, the initial velocity is 0. The rock is dropped. We know when you drop something, it starts at rest. Hasn't picked up speed yet. For the ball, this is thrown downward. So our initial velocity in the y is going to be that velocity it's thrown down with times our sine of theta. We don't actually have to do any math here. This is just a proof of concept. It's thrown down. That means it's going to have some amount of initial velocity, and that would be negative since it'll be downwards. The acceleration for both of them, the ball and the stone, is negative 9.8. They have the same starting point. They're both falling the same distance. They have the same acceleration, but the ball just has a velocity downward right at the start. So that means the ball is going to hit the ground first. All right, let's get into our last problem, number 17. This one is a bit of a doozy, so let's go through it together. A ball is launched from a 75-meter tall cliff. The ball is thrown at an initial velocity of 35 meters per second at an angle 58 degrees above the horizontal. Determine the time the ball spends in the air and the distance from the base of the cliff that the ball lands. So let's first identify what are we actually solving for. We want to determine the time the ball spends in the air, so that's our time, the total time in particular, and we want to find out the distance from the base of the cliff that the ball lands. So we know it's an angled launch. It's going to follow a parabolic trajectory, like so, all the way down to the ground. Here, this distance, all the way to where it lands, is going to be our delta x. That's what we want to solve for. That's the distance from the base of the cliff that the ball lands. Here, we've dealt with angled launch problems before. The main difference is we've always done angled launches where we are landing at the same level we were launched from. Here, we are doing an angled launch off of a cliff, so we're landing lower than where we started. So let's see how should we tackle this. Well, we still want to start our same way. We always want to start off for our projectiles with our XY chart, separate out our variables. It's going to be in the air, so we know the acceleration in the x. There's no forces that direction. We get our 0 meters per second squared. In the y, we have our force of gravity, causing that negative 9.8 meters per second squared acceleration. We are given, right here, we're given this height. That is our delta y. So let's plug that in as well. We know the delta y, where we're really falling here, that is going to be 27. We'll say negative 27. Now, what we can do, since we have an angle, is we can break this up into our initial velocity in the x and our initial velocity in the y. Let's draw our launch velocity down here just so we have a bit more room. What we're saying is that this initial velocity is given as 35 meters per second. We can break this up into components and say we have this component in our x direction, some initial velocity in our x. We have some component in our y direction, our initial velocity in our y. And we have equations for these. We know that our initial velocity in the x is just the velocity times the cosine of our angle theta. Our initial velocity in the y is our initial velocity times the sine of our angle theta. And now we can go through and just plug these in. The velocity, 35, times the cosine of our angle right here is 58 degrees. Let's go ahead and plug that in. So our angle is 58, velocity is 35. Let's remember that. We'll go over to our calculator. So the angle, I've already forgotten, is 58. So we'll say cosine 58. And we're multiplying by that velocity 35. So 18.55. Velocity in the x, 18.55 meters per second. Let's do in our y direction. Here, we're saying, again, that velocity, 35. The angle is 58. We're just using sine this time. So you want to say sine of 58. Multiply that by 35. 29.68. And that's our initial velocity in the y. Let's add these into our table. That initial velocity in the y is going to be 29.68 meters per second. Our initial velocity in the x is going to be our 18.55 meters per second. Now, at this point, what we can do is we can solve for the time it takes for us to actually land. Something I want to point out here, for problems like these, oftentimes we've given you the approach that you have to identify the peak of your arc and figure out, oh, at that peak, you know the final velocity is going to be 0. That is absolutely true, but what we're doing here is, since we know our delta y, we are changing our position. At our start, we are right here. Our position at the end, we are falling down 27 meters. So our position is going to decrease by 27 meters. That gives us this delta y that we can use. That allows us to solve for our total time. What we can do then is say, well, we have a delta y, an initial velocity, and acceleration. We're looking for our time. Let's use our equation. Delta y is equal to our initial velocity in the y, multiplied by our time, plus our 1/2 acceleration in the y times squared. We're just going to go through, and we can plug in our information. Here, you would have to use the quadratic formula. So another option, if we're looking at all our equations, final velocity is equal to our initial velocity plus the acceleration times time. We also have the final velocity, and these are all in the y direction. Final velocity squared is equal to our initial velocity squared plus 2a y delta y. So here, the one thing we're really missing is that final velocity. If we find our final velocity, it makes it easier to solve for time. If you want to avoid that quadratic formula that we'd have to use right here, what you can do is we can just say, let's use this equation right here. Since we have our delta y, initial velocity and acceleration, plug everything in, solve for that final velocity, and then use that final velocity and plug it into our top equation right here and solve for your time. Much, much easier. Okay, let's go ahead and do that. Let's move our equation right here, just off to the side for now, so that we can use this equation and plug everything in. Okay, let's go with blue, just to differentiate it from what we're doing. Alright, so we'll start off. We have our final velocity in the y squared, initial velocity in the y squared. Let's plug in our 29.68. We're going to square that. 2 times our negative 9.8 times our negative 27 delta y. Alright, and now we just have to go through, use our calculator, help us find this out. 29.68 squared, that gives us 880.9. Then 2 multiplied by 9.8 multiplied by 27 gives us 529.2. Since we're multiplying a negative by a negative, those negatives cancel out. That's why our 529.2 is positive. And now that's equal to our final velocity in the y squared. Let's add those two together. 880.9 plus 529.2 gives us, if we plug it into our calculator, 1410.1. That's still equal to our final velocity squared. We need to get rid of that squared, so let's take our square root on both sides. On the left-hand side, the square root cancels with the square, and now we just need our square root of 1410.1, which is 37.55 meters per second. Alright, we get our final velocity. That's how fast we are going in the y direction. Now, there is something we should recognize about this situation. When we have gone this far, this velocity, this is our magnitude, 37.55 meters per second. That's our magnitude. We know when we are falling, right about to hit the ground, we are going to be moving very quickly downward. So this is not a positive velocity. This is our negative velocity. We're taking the square root, so we can't tell. We're always going to get a positive, but we know this has to be negative since we'll be moving downward. Alright, so now we have our final velocity. Let's go ahead and add this into our y column. Final velocity in the y, negative 37.55 meters per second. Now, let's use our top equation that we have right here in pink. Let's use that and solve for our time we're spending in the air. So we are going, let's rewrite our equation right here. Final velocity in the y is our initial velocity in the y plus our acceleration times time. That final velocity, negative 37.55. Initial velocity, 29.68 plus our acceleration of negative 9.8, and we're solving for our time. Again, this is a negative out front, don't want to forget that. Let's go ahead, isolate our variable time. You want to start off, let's move our 29 over. We're going to do that just by subtracting the 29 from both sides. That's going to cancel it on our right-hand side. And now we have to do our 37.55 minus our 29.68. Since they're both negative, the absolute value is going to get bigger. That gives us negative 67.23 is equal to negative 9.8 times our time. And now we just have to divide both sides by that negative 9.8. It cancels on our right-hand side. And we just say, since our negatives are going to cancel as well, on our left-hand side, 67.23 divided by 9.8 gives us our time, and this is our total time, of 6.86 seconds. Okay, that's our total time. Now, we can plug that in for our x direction, and we are able to solve for what we want, that delta x. Let's go ahead and box our answer. We're able to solve for our delta x using the equations we've used so many times. our delta x is equal to our initial velocity in the x times time plus 1/2 the acceleration in the x times squared. Since the acceleration in the x direction is 0, this whole term cancels out, goes to 0, and we have delta x equal to our initial velocity. Let's plug it in, 18.55. Just pulling it from our data table. In our time, 6.86. If we go ahead and multiply these together, 18.55 times 6.86, that delta x is 127.25 meters. All right, there we go. Here is our answer. Now, if we do a different method, and there's multiple ways you could solve this, you didn't have to identify right here. You didn't have to identify that you're falling down 27 meters. What you could do is you could treat it just like our typical angled launch problems, and you could say, oh, we know right at the top, this velocity in the y direction is 0 meters per second. If you do that, you can solve for the time it takes to go up, the time it takes to reach the peak. You can use that then to solve for how high up it goes. This could be your delta y. You could solve for the height at the peak and get your time it takes on the way up. What you then have to do is split it into another problem and say, now that we figured out how long it takes to go up, we have to figure out how long it takes to go down. And you essentially treat it like a horizontal launch problem, but now you're starting at whatever this delta y is in red, whatever this height is, plus your 27, because you are going purely to the right here. Your initial velocity in the y direction would be 0. You're going purely to the right. You are going to fall down this height you calculated, and then you are going to fall down this 27. So your total delta y will be both of those added together as you fall down all the way to the base of the cliff. You could then calculate the time it takes you to fall down and add it together with the time it takes you to go up. You'll get the same answer either way, but it's just two different ways, two different approaches you can take. All right. Hope this helped.